In this lecture and two others, we talk about a remarkable sequence of numbers called Catalan numbers. Catalan numbers. So that's a sequence C0, C1, C2, C3, C4, starting with ones, and then it goes as 2, 5, 14, 42, and so on. And it appears in many problems in mathematics, and I want to discuss a few of their incarnations today. And in the next two lectures, we will discuss an explicit formula for these numbers. So they were discovered, at least one of the versions is that they were discovered by Leonhard Euler. And Euler was studying the following questions. So let me start with the first sort of interpretation of Catalan numbers. And this is related to triangulations of a polygon. Triangulations of a polygon. Okay, so what is a triangulation? So let's consider a polygon, and for a certain reason I will take a polygon P. So P is a polygon, P is a convex polygon with n plus 2 sides. So convex means for every 2 points, a segment connecting them is inside the polygon. So that's an example of a non-convex polygon, and that's an example of a convex polygon. So this one is not convex because you can connect 2 points by a segment which is outside of the polygon. So P is a convex polygon with n plus 2 sides, and you can ask why not n? That's related to the way I label Catalan numbers. So, and then what is a triangulation? So it's a little definition. So a triangulation of P is a decomposition of P into triangles by non-intersecting diagonals. So let's draw a triangulation of this one, so something like this, maybe this. So just draw a collection of diagonals so that they cut it into triangles. Okay, so maybe a little exercise for you to think about is that every triangulation of P has how many triangles? So a triangle has one triangle in triangulation, so for n equal to 1, it's 1, for n equal to 2, it's 2, so has n triangles. So that's a little exercise. So for instance, if you have, okay, let's go through different polygons now. So, and then Cn is a number of such triangulations. So now it's easy to compute it for small n's. So let's start with C0. So C0 is a triangulation of a 2-gon, and I will put it equal to 1. That's more or less by definition, because it's not exactly clear how to triangulate a segment. And C1 is obviously 1, and the picture is, of course, just this. It's dead. A triangle. So C2 equals to 2, and the reason is because we can cut a square in two different ways into triangles. By the way, I said a convex polygon, and it does not depend on which convex polygon you take. So moving slightly the vertices of a polygon does not change the number of triangulations. So the next interesting case is C3 equal to 5, And for this, you can take a picture which is a 5-gon. And if you take a pair of diagonals, they will always contain one vertex. And so basically, there are 5 triangulations which are obtained one from another by a rotation. So, and 2 more are these. And, oh, sorry, this was already taken. So 2 more, this one, and starting with this vertex, this one. So these are 5 triangulations. So as I said, C4 equals to 14, and this starts to be a little bit more tricky. So let me now erase all of that, and I will compute C4 and C5, and then we'll see the general pattern. Okay, so so far again we have C0 equal to 1, that's a D-gon, C1 equal to 1, C2 equal to 2 triangulations of a 4-gon, C3 equal to 5 triangulations of a 5-gon. So what about C4? So C4 is still doable by hand, that's a 6-gon, and again, so one way to cut it into triangles is just choose a vertex and draw 3 diagonals out of this vertex. And there are basically 6 ways to do it if you just rotate it. So there are 6 different ways to cut it in this pattern. So another pattern one can do is basically to cut into 4 gons and then cut each into triangles, but so that the diagonals have distinct endings. And again, there are 6 ways to do it. And finally, there are 2 ways which are which have a triangle in the middle and 3 ears. So 2 ways. One can do this or rotate by 2 pi over 6. So in total we have 14, and you see that it starts to be a little tricky. So how shall we compute C5? So let's take a 7-gon, and I will draw a 7-gon with one side which is kind of special. I will draw this side as a base side. And then here's a 7-gon. So now let me maybe label vertices 0, 1, 2, 3, 4, 5, 6 or something. And then for every triangulation, there exists at least one, exactly one triangle, which is adjacent to the edge 0, 6. So picture is like this. So at least one triangle has 0, 6 as an edge. That's an easy exercise. So okay, let me maybe say it a little later in general. And then, so after we choose which is the 3rd vertex of this triangle, then we need to triangulate the left-hand side and right-hand side. And so basically we just need to go through a few options. So first we can imagine that our triangle is actually 0, 1, 6. And then the number of triangulations is just the number of triangulations of the remaining 6 gone, if we cut this triangle away. And so we get that C5 equals to, let me say, C0 times C4. And C0 stands because on the left-hand side of this triangle, there is exactly a diagon. So that's 1. And then another option is that we have a triangle 0, 2, 6 here. So then here we need to triangulate a triangle. And there is C1 options to do that, which is still 1. And on the right-hand side, we'll see that we need to triangulate a 5-gon, so we multiply it on C3. And we continue, so we have C2, C2, C3, C1, C4, C0. And each of them corresponds to one of the pictures, so that's basically kind of this picture, this picture, this picture, this picture, and this picture. And if we now compute it, so this will give us C0, C4 is 14, plus C1, C3 is 5, plus C2 squared is 4, plus 5 plus 14, and this is 38, 40, 28, 38, 42. So we have computed C5, so now C5 is 42, and of course this method is rather general. So let me just state this proposition. So proposition is that the following recurrence relation holds. So if we want to compute Cn, that equals to C0 Cn minus 1 plus C1 Cn minus 2 plus and so on plus Cn minus 1 C0. And the proof is, of course, just repeat the same argument. So so let's try to kind of see what it looks like in general. So we have a polygon, and this is a n plus 2 gon. And we take this n plus 2 gon with a fixed base, and then we look at triangulations having a particular triangle adjacent to this base line. And then we can assume that this is a plus 2 gon, and this is b plus 2 gon. And so basically Cn will equal to the sum Ca times Cb, and then the question is only what is the condition on this A and B, and clearly the condition is that A plus 2, which is the number of sides here, plus B plus 2, which is the number of sides of the second polygon, this gives the number of sides of the big polygon plus 2 minus 1. So it's n plus 2 plus 2 this sides minus 1. And this means that A plus B is n minus 1. And so we sum up Ca Cb over A plus B equal to n minus 1. And of course, we'll start with these two gons at the endpoints. So it means that A and B are greater or equal than 0. So that's it. That's the proof. Okay, and so this recurrence holds, and so of course it gives a way to compute all other Catalan numbers. So there is a unique sequence defined by this recurrence plus the first two terms, for instance. Okay, so in a way we found a way to compute Catalan numbers, and to move on, let me give another interpretation of Catalan numbers based on parentheses and expressions with parentheses. So let me move to this second topic now. Now I want to talk about the second interpretation of Catalan numbers. So it's related with expressions with brackets. So consider a sequence of brackets. So what I mean is that we have opening bracket and closing bracket are kind of possible elements, and then we just consider a finite sequence where we have a collection of a sequence of opening brackets, maybe then some closed brackets, some opening, some closed, closed opening, or something like this. That's a sequence. So consider a sequence of brackets like this, and then so call such sequence admissible if two conditions hold. So first, number of opening brackets equals to the number of closing brackets. And second condition is that in every initial subsequence, number of opening brackets is greater or equal to the number of closing brackets. So let me give you some examples. For instance, if you take a word like this, that's not admissible, because the number of open brackets and closed brackets is equal to each other, it's equal to 3. But if you take initial subsequence like this, so initial subsequence means just the first couple of terms. Then this one has 2 opening and 3 closing brackets, so this equation is violated, inequality. And for instance, if you do something like this, that's admissible. So where this idea comes from, so imagine you have arbitrary kind of expression, a plus b times, I don't know, c plus d, a plus c plus a, I don't know. If you take any expression like this and then delete all variables and just leave the brackets, you will get a word in brackets. And obviously this will be an admissible word. And the reason is because basically a word is admissible if you can pair brackets so that sort of inductively one can evaluate certain brackets which are the closest to each other and forget about them, and so on and so forth. And that's a technical way to say that. So you can contemplate on that a little bit. So let's now prove the following proposition. So proposition is that number of admissible sequences with 2n brackets, so n opening and closing, equals to Cn. So first a couple of examples. So if you do, for instance, n equal to 1, it means you have 1 opening bracket, 1 closing, and so you have to start with opening bracket because the number of opening brackets in the initial subsequence should be bigger or equals than closing, so it has to be 1 at least. And then, of course, we put the second closing bracket, and that's it. And this is the only thing we can do with 2 brackets. For n equal to 2, there are 2 options. So one can either do opening, opening, closing, closing, or opening, closing, opening, closing. So this is something like, 2 plus bracket 3 plus 4, and this is something like 2 plus 3 bracket 3 minus 5. I don't know. So for n equal to 3, there are more patterns, and if the theorem is true, it should be 5. And indeed, so we can have either all of them are kind of nested, or the picture is like this, oops, or like this. What else? So of course, all 3 can be going one after the other. And finally, the last option is that there are 2 pairs inside a big bracket. And you see that this is 1, this is 2, this is 5, and we see a sequence of Catalan numbers. So how to prove it? So the proof is based on the following idea, that this number, so call this number, I don't know, this number of admissible sequences satisfies the same recurrence. And the idea of how to prove it is very simple. So you just take an admissible sequence, so for instance this one, and then you look at the first bracket. And then there is a corresponding closing bracket. So the number of opening brackets is in every initial sequence greater or equal than the number of closing brackets, and eventually equals. So we can sort of go adding bracket one after another until it equals for the first time. And this is the corresponding closing bracket to the first opening bracket. And then we know that we will see some correct bracketing expression for everything which stands between these 2 brackets, and some correct bracketing expression afterwards. And that exactly gives the same inductive formula. So here, the first bracket is here, the last is here. And so, okay, so this is C1 is 1, C2 is 2, and here we have that this term corresponds to, so this and this term corresponds to C2 times C0, because inside of these big brackets we have two pairs, and there are two ways to write a word with them, and after this pair of brackets there is nothing. And this picture corresponds to the case when we have one inside and one outside, and this is C1 square. And finally, these two correspond when we have 0 inside here and 2 outside, and so this is C0 times C2. And so we see exactly the same pattern as in the previous case. So this number satisfies the same recurrence formula, and thus equals to the sequence of Catalan numbers. So that's the idea of the proof of the proposition. So in totality, we have seen two interpretations of Catalan numbers with number of bracketing expressions and number of triangulations of a polygon. And an interesting question is how to construct a bijection between two. So suppose you have a triangulation of a polygon, how to write down the corresponding bracketing expression. So let me leave this question for you to think about. So maybe a complicated exercise with a star, construct an explicit bijection. Between 1 and 2. Also there will be some problems in p-sets about that and some other interpretations of Catalan numbers. But I want to move a little bit forward and using the second interpretation come up with the explicit formula for Catalan numbers. And this is what the next lecture is about.